This is the last video for this unit, and it's going to be on concavity. So for concave up, we've touched on this a couple times, but just to recall it, concave up occurs when the average rate of change over equal length input value intervals is increasing for all small length intervals. So if you think back to the first time we really talked about concavity, I talked about basically sampling this little interval and then sampling this tiny interval and then this one and this one. And I slapped a value on it, like this was -10, -5, +5, +10, okay? So that's what this is referring to, except the intervals are really small, and we want to compare them, and they need to be the same. So that's what equal length input value intervals means. It's talking about the x values, okay? So concave down is going to have the same description, but instead we'll have it decreasing. So the average rate of change over equal length input value intervals is decreasing for all small length intervals. Okay, so example 20, selected values of the functions k, m, and p are given in the tables below. For each function, determine if the function could be concave up, concave down, or neither over its domain. So for concavity problems, you will always use average rate of change, all right, or your difference quotient. You never just want to compare the outputs, okay? So you always want to use the difference quotient, which is our y2 minus y1 divided by x2 minus x1. All right, so let's start with function k of x. Okay, so we'll start with this first pair of points. We're going to have 1 minus 4 divided by 1.1 minus 1. So 1 minus 4 is going to be -3, and then 1.1 minus 1 is 0.1. So you're not going to have a calculator, okay? So if you think about this, there's a couple ways you can approach this. A, think of that decimal. You're multiplying, or I'm sorry, you're dividing -3 by 0.1. So you're going to move the decimal over one spot to the right, okay? Or you can think of it as fractions. 0.1 is the same as 1/10. Okay, and I think you guys learned a phrase, keep change flip. You're going to multiply with the reciprocal of the denominator. So -3 times 10 over 1, that also gives you -30, okay? So you can either think of moving the decimal, or you can keep change flip and multiply with the reciprocal of the denominator. Now from here, we'll have -1 minus 1 divided by 1.2 minus 1.1. So we can see that the inputs, they have a difference of 0.1. So we're always going to be dividing by 1/10 or moving that decimal over 1 to the right, okay? So now I have -2 divided by 0.1, which is going to be equal to -20. Down here, I have -2 minus 1. Sorry. That should be -2 plus 1, because it's -2 minus 1, or minus -1, which would be plus. And then this will be 1.3 minus 1.2. So we end up with -1 divided by 0.1, which equals -10. So if we look at this, we go from -30, -20, -10. And if we compare those values, we go +10 and +10, which means over these small length intervals, the average rate of change is increasing by 10 each time. okay? So that means this is concave up. So concave up because the average rates of change are increasing over small length intervals. Okay, now let's try m of x. So we'll take the average rate of change. So we'll have 4 minus 1 divided by 1.1 minus 1. So we end up with 3 divided by 0.1. Just like from the last problem we saw, we'll end up with 30, but it's positive this time. Second set, we have 7 minus 4 divided by 1.1 minus 1.1. So we end up with 3 divided by 0.1. We get 30 again. And this last part, we have 10 minus 7 divided by 1.3 minus 1.2. And again, we get 3 divided by 0.1, which is equal to 30. So in order for a concavity to occur, the average rates of change over these small length intervals have to either be increasing or decreasing. This is constant, all right? We have plus 0, plus 0. Therefore, this is neither. So neither because the average rates of change are constant over small length intervals. And the last one. So same approach for concavity. We'll have 7 minus 1. This has the same inputs, so I'm just going to divide by 0.1. Okay, so we end up with 6 divided by 0.1, which is equal to 60. The next set, we have 11 minus 7 divided by 0.1. 11 minus 7 is 4. Divided by 0.1, we get 40. And down here, we have 13 minus 11 divided by 0.1, which is 2 divided by 0.1, so we get 20. Now, if we look at this one, we have minus 20, minus 20. So therefore, over these small intervals, the average rate of change is decreasing, which means we have concave down. So concave down because the average rates of change are decreasing over small length intervals. All right, and that concludes this first part. So I hope these were helpful.